So in this video, what we're going to do is talk a bit more about the ordering on the ordinals. So just as a recap or recall, so from last time. Well, we gave this definition that if we had two ordinals, we said that alpha was less than beta. Alpha and beta are ordinals. This is true if and only if alpha was an element of beta. And I guess one of our short-term goals right now is to prove that this ordering is linear or total. So in other words, if you take two ordinals, they're either equal or one is less than the other or vice versa. So how do we prove this? Well, one step towards this is proving a nice characterization of not the strict less than, but less than or equal to. So with this definition, when we say alpha is less than or equal to beta, what we mean, I guess by definition, would be that either alpha is an element of beta or that alpha is equal to beta. And so what we're going to prove this time, so this is a lemma, is that so maybe we'll use different, or maybe we'll use different Greek letters. So maybe we'll assume that if if gamma and delta are ordinals, then what's the result? Well, the result is that alpha is less than, or gamma is less than or equal to delta. This is true if and only if alpha is a subset of delta. So this is kind of nice. The definition of this less than is in terms of being an element of, and of course there's some relationship between being an element of and being a subset of, but they're not the same thing. But for ordinals, kind of being less than or equal to is kind of the same thing as just being a subset. One of the consequences of this is going to be, so this is going to imply that, well, if you had that gamma, say, was a proper subset, maybe we could write it like that, maybe we could write it like this, so it's a proper subset of delta, then it's actually going to be the case that gamma is an element of delta. And well, you also have the reverse, right? If gamma is an element of delta, well then, since delta is transitive because it's an ordinal, it'll be a subset of just kind of justify the backwards direction. Well, gamma is an element of delta. Well, this implies that gamma is a subset of delta because gamma is because delta is transitive. But well, if gamma was equal to delta, so but gamma is not equal to delta, because then that would imply that delta is an element of itself, because if gamma is equal to delta, then delta would be equal to gamma. Delta would be equal to gamma, and then would be an element of itself. So maybe this isn't an S; it's a delta. Okay, so. All right, so this is what we're going to prove. We're going to prove this big lemma here, that being less than or equal to is equivalent to just being a subset. So how do we kind of maybe approach the proof of this? One of the directions, so this forward direction is not that much work. The trickier direction is going backwards. So what's the proof? So this forward direction is, well, if we assume that gamma is less than or equal to alpha, well, I guess there are two options. Then either, well, by our definition of less than or equal to, then either gamma is an element of delta, but then because delta is transitive, it's a transitive set because it's an ordinal, we'd have that gamma is a subset of delta, and so then we'd be done, right? That's what we'd wanted to prove. Or, well, gamma is equal to delta. Oops, sorry, not as an element of, or it's equal to delta. But that's also, I guess, we'd be done as well. So in either case, we'd be good. All right, so that's the forward direction. Well, what's the backwards direction? This is the trickier direction. So we want to assume that gamma is a subset of delta. And well, we'd be done if gamma is actually equal to delta. So assume that gamma is actually a proper subset of delta, right? Because if it was equal to delta, well then, well, it would be less than or equal to itself, and so we'd be done. Using our definition of what less than or equal to means. Being less than or equal to in this context means that it's either an element of or equal to. So we can assume that it's not equal to. And so what we'd have is we'd have that gamma is a proper subset of delta. And maybe before we kind of proceed, maybe we'll draw a little bit of a picture. So given that we haven't proven that this ordering on the ordinals is total, yet maybe there's a little bit that needs to be justified about this picture. But let's assume for a second that they actually did come in a line. What kind of thought do I have in my head when we're going to walk through this argument? Well, the smallest ordinal is going to be 0, and then they have 1 and 2 and so on. And then at some point we're going to get to this ordinal. We're going to get to this ordinal gamma, and maybe delta is out here. And why would we know this? It's because, well, delta is not going to be equal to gamma. And well, if this is the case, that these two things are not the same, we can look at maybe all the ordinals that come, I guess, either at gamma or after it. So in other words, what we're going to do is consider the set of all. So if we look at all these green dots, one way to classify all these green dots is saying, well, this is going to be the set, maybe we'll call it S. This is going to be all the elements of delta. This is going to be all the elements of delta that aren't elements of gamma. So all the elements of delta that aren't elements of gamma. Why is this the case? Well, it's maybe exactly because, or one way to think about this is, well, what is an ordinal? We talked about last time. An ordinal is the set of all ordinals that are elements of it, right? It's all the ordinals that come before. So in other words, well, if you were less than gamma, would have to be that, well, you're an ordinal and you're an element of gamma. And so this collection of sets, all the stuff to the right, that's just going to be everything that's not an element of gamma. And, well, what are we going to say? This is a subset of delta, and delta is a well ordering, so it's going to have some least element, and, well, that least element we're going to prove is equal to gamma, right? Well, why? Well, everything that's less than gamma, I guess, by definition would be an element of it. So that's maybe the intuition for what we're about to do. How does the argument go? So maybe we'll write this down. So let's define the set S to be all of the elements, say alpha, in delta that aren't elements of gamma. And, well, since gamma is a proper subset of delta, so since gamma is a proper subset of delta, it must be the case that S is non-empty. So it must be that S is non-empty. Right, just writing out the definition of what it means to be a proper subset. Is there some element of gamma that is not in, there's some element of delta that's not in gamma. That's just what being a proper subset would mean. Okay. So what can we say from this? So what do we have? We have the set S, which is a subset of delta, and it's non-empty. Delta is a well ordering, since delta with the epsilon ordering is a well ordering. So delta is well ordered by epsilon, so is a well ordering. Well, S must have some least element. There is some least element. Let's call it maybe beta. So again, what does this mean? So by least, we mean epsilon least, or maybe less than least. What does this mean? This means that, well, beta is an element of S, and every other element of S is bigger than or equal to beta. We'll write that down. So what do we know? We know that, well, for every other maybe for every other alpha in S, it would have to be the case that beta is less than or equal to alpha. And again, this is using our original definition of this is using our original definition of the less than or equal to. Okay, so what's our claim now? What's our claim now? And this is gonna, once we prove this claim, this is gonna be enough for this direction. Well, we want to prove that there's some least we know that there's some least element S because because delta is a well ordering. We want to prove that gamma is actually equal to beta. And if we can do this, we're done, right? Because if we prove that they're equal, well, by definition, beta is in S, and also by definition, all of S's elements are in delta, right? And so if we can prove this, then we'd win. So how does the proof of this go? Well, we can show that, well, gamma is a subset of beta and vice versa. Maybe the first direction, maybe the first claim, so subclaim 1 maybe, is that beta is a subset of gamma. How can we prove this? Well, let's assume that we have some alpha that's in beta. And well, what we want to prove is that alpha is actually in gamma. Well, but one thing that we can say is that, well, if alpha is in beta, it can't be that alpha is in S. And so note that alpha is not in S. Right? Because, well, just writing out what it means for beta to be, I guess, the least element of S, or the epsilon least element of S. Every element of beta can't be in S. Well, what does it mean to be in S? It means that you're in delta. So in other words, what does it mean to be in S? It means that, well, to be in S means that you're in delta. So what we know is that either alpha is in delta, is not in delta, sorry, or, well, the definition of S was all the things that are in gamma. So in other words, either alpha is not in delta or alpha is in gamma. But why do we know that alpha is in delta? It's exactly because delta is transitive. So note further, maybe I'll say further. What do we know? We know that alpha is an element of beta, which is an element of delta. Delta is a transitive set because it's an ordinal, and so that means that alpha is an element of delta. So alpha is an element of delta. But if alpha is an element of delta, and we know that it's not an S, it has to be that alpha is in gamma. So alpha is in gamma. But that's what we wanted to prove, right? This is the end of claim 1, right? Because we just took an arbitrary element of beta and argued that it was actually in gamma. That's our first claim. Our second claim is, well, we need to show that if we take an element of gamma, it's actually in beta. So we can say something like, well, if we take some element of gamma, well, the trick here is to observe, well, if alpha is in gamma, we know that if alpha is in gamma, it must be that alpha is in delta. Why is this true? So it's not because gamma is an element of delta. So kind of maybe the warning here is this is not because, not since alpha is an element of delta, right? We're trying to prove this. But what are we assuming in this argument or in this direction? We're assuming that gamma is a subset of delta. So since gamma is a subset of delta, but since gamma is a subset of delta. So since gamma is a subset of delta, we have some element alpha in gamma, it has to be in delta. Well, what else do we know? Well, by definition of beta, beta is also going to be in gamma. So also, we know that beta is an element of delta, right? Because beta is an element of S, and by definition, S is all the elements of delta that satisfy some property. Well, what can we say now? Well, delta with the epsilon with the membership relation, that is a well ordering. So in other words, it's total. So note. So we can say maybe since delta with the membership relation is total. Well, there are three options, and we're going to argue that two of them are impossible. So since this thing is total, what do we have? We have that either, well, we're going to compare alpha and beta, which are both elements of this total ordering. So either alpha is an element of beta, which is what we'd want, right? This is our dream. So this implies that we're done. And we're going to argue now that the other two cases are impossible. So the other case would be alpha is equal to beta. And then the third case would be that, well, beta is an element of alpha. Well, why is it the case that that alpha can't be equal to beta? Well, if it was equal to beta, what do we know about beta? Beta is in S. So that would imply that alpha is in S. But what is S? S is the set of all things that aren't in gamma. And so that would imply that, well, alpha is not in gamma, which is a contradiction because we're assuming that alpha is actually in gamma. So this would be a problem. So this would be a problem. So it can't be that this case is possible. And then why can't the other case be possible? So if we had some element of, if beta was an element of alpha, well, what would have to be the case? It would have to be that, well, we'd have that beta as an element of alpha, which is an element of gamma. But gamma is an ordinal, so it's transitive. So that would mean that beta is an element of gamma. So beta is an element of gamma. But why is this a problem? Well, it's because beta is in S again. So beta is in S, which means that it can't be an element of gamma. So in other words, this would imply that beta is not an S, which is also a contradiction. But then we're done, right? Well, this is the end of claim 2. So I guess just one last line. So what did we just prove? So gamma is equal to beta, but beta by definition is inside of delta. So beta is in delta. And so I guess what this implies, maybe one last line. So gamma is going to be less than delta, which is what we wanted to prove. Well, we wanted to prove that if we have a subset of, if we have an ordinal that's a subset of delta, then it's actually an element of delta as well. I guess one comment about this argument. So note, this statement only is true for ordinals. So we are not saying that if A is a subset of delta, then A is an element of delta. We are not saying this. What we are saying is that if we have a subset of delta and the subset happened to be an ordinal, then it would actually be an element of delta. So we must assume that A is an ordinal. Right? If we just take some subset of delta, doesn't mean that it's going to be an element of it, because that would imply that it's an ordinal. But if we had that it's an ordinal, then it actually would be an element of delta. Okay. So what we'll do in the next video is prove that the ordering on the ordinals is total. So in other words, if we take two ordinals, either one is less than the other, or they're the same. And then what we can do, one of the consequences of this is we can give a proof of the Burali-Forti paradox, as I think that's what it's called. And what is that the claim? That's the claim that there's no set of all ordinals.